Okay, so we're kicking off the spring 2013 semester by revisiting this concept of the definite integral. Welcome back to class, everybody. Hello. So I want to just begin. By the way, my camera is low on batteries, and so it's probably going to die sometime during this this video. But whatever, such is my life. Okay, so here's the definition of the definite integral. We have f is a continuous, let's just say a continuous function on the interval from a to b. We divide this interval from a to b into n. N is just going to be some arbitrary integer. N into n subintervals of equal length. And we refer to this length as delta x. In order to divide an interval from a to b into n pieces, we take the length of the whole interval and divide by n. Then we assign an ordering to the endpoints of the subintervals. So we have x1, x2, x3, up to xn minus 1, and then xn is b. So these are the endpoints of the n subintervals. So you could imagine something like this. If this was our interval from a to b, then x0 would be a, xn would be b, and then we go forward x1, x2, x3, and so on up to xn minus 1. Okay. And the formula for the endpoint, for the I endpoint, is just going to be a plus I times delta x. So that is a plus I times b minus a over n. Let me make sure that the camera is getting all of this. Okay, it's getting all of it. Good. So these are our endpoints. And then we choose xi star is any point in the interval, we'll say xi minus 1 xi. Okay. These are called sample points. Okay. So we have divide into subintervals, set up the endpoints of the subintervals, and pick sample points in the intervals. And then we can form the Riemann sum. So the Riemann sum, okay, R-I-E-M-A-N-N, say it with me, Riemann. Okay, Riemann. The Riemann sum is the sum where we let I go from 1 up to n, and we take f, and we evaluate f at the sample point, and we multiply by the width. Okay, so this is the Riemann sum for n pieces, and then the integral, this is the definite integral, it's denoted like this. This is what we get when we take the limit as n goes to infinity. Okay, so we take a Riemann sum with n pieces, and then when we let the number of pieces go to infinity, we get the definite integral. So if this limit exists, then we say f is integrable. Okay, so this is the definite integral. This is the definition of the definite integral. Let's just quickly go through some notation here. So this this symbol right here is called the integral sign. Okay, A and B are called the limits of integration. And f is called the integrand. Say that with me, integrand. Okay, and I should point out that x is just a placeholder. So x is a placeholder. This semester's off to a smashing start. My pen is running out of ink here. X is a placeholder, so what that means is that all of these notations stand for the same thing. So if I integrate from a to b f of x, that's the same as integrating a to b f of t, and that's the same thing as integrating a to b, let's say, f of w, and so on. Okay, so the letter that you see in here, x, t, w, it doesn't matter. Okay, all of this means exactly the same thing. Well, what is the interpretation of this integral? Let me pause while I get another pen. Okay, what is the interpretation of this integral? Well, here's a picture. Say a, b. I'll just draw any old graph I like from a to b. Okay, let's divide this into some pieces. Maybe I have other colored pens that I can work with here. I'll try this bright red pen. Maybe this will work. I use this to grade all my exams, so some of you might think this is looks familiar. Okay, let's just divide this into, I don't know, six pieces. Okay, so there's 1, 2, 3, 4, 5, 6 pieces. So this is x1, x2, x3, x4, x5. And of course, this would be x6, and this would be x0. Okay, I'm just gonna use the right-handed endpoints to be the sample points in this case. So so let's take xi star to be the right-hand endpoints. Okay, so each of these intervals has length delta x. Delta x is equal to b minus a, in this case, over 6. So that is n equals 6 here. And if I take the right-hand endpoints, then I map each of these to the graph, like so. And I'm going to form rectangles here. So here's this endpoint for x2 forms a rectangle that's under the x-axis. This also forms a rectangle that's under the x-axis, and so on. So what our Riemann sum is it counts these rectangles above the x-axis positively, and these rectangles below the x-axis negatively. So the sum, I going from 1 to 6, of f of xi star delta x, this is equal to the sum of the signed areas of these rectangles. The 6 rectangles. Okay, so this is the so this is what the Riemann sum represents in this case when x equals 6, or when n equals 6. If we were to allow that 6 to become larger and larger, then these rectangles would become thinner and thinner, and there would be more and more of them, and you would get an approximation to the actual area under the graph. So the definite integral in this case from a to b would be the signed area under the whole graph. So in our picture here, it might look something like this. Let's draw it in. Something like this. So you'd get the actual area. These regions above the x-axis counted positively, this region below the x-axis counted negatively. So that is the interpretation of the definite integral. All right. I should talk a little bit about these Riemann sums. These are, so the summation notation rules, we have some rules for sums here. The first rule is that if you take a constant, so c is a constant here, then this is equal to n times c. Okay, why is that? So example, so suppose you took the number 7, 7's a perfectly good constant, and you summed up to, well, let's do 5. Then this would be what? 5 copies of 7. Okay, so that is, so this would be 5 times 7. All right, that's rule number 1. Rule number 2, c is again a constant here. If you take any summation that looks like this, well, the constant is just being multiplied by every term in the sum. So this would be c times a1 plus c times a2 plus dot 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 plus all the way up to c times an. So this would be equal to c times the sum of these and so that is equal to c times the summation. Okay, like so. The third rule is that if you're adding or subtracting terms in a sum, then you can split this into the sum or difference of 2 different sums, like so. Okay, we'll talk a little bit about this in class if people have trouble with those rules. All right, let's do an example, or well, maybe I'll start off with a theorem. So theorem, if f is integrable, then using right-hand endpoints, for the limit gives the integral. Okay, so what that means the integral from a to b of f, you can think of it as the limit as n goes to infinity, the sum 1 to n, and then we can take xi to be, so xi, we can take this to be a plus I times delta x. This is our formula for the right-hand endpoint. Okay. All right, so that's a theorem. So we'll just use the right-hand endpoint definition of the integral from now on. Okay, so let's do an example where, so find the Riemann sum for the function f of x equals x cubed. So this is going to be a 2-part example. So part 1 is find the Riemann sum for the function x cubed minus 6x over the interval from 0 to 3 with n equals 6. Let's make this a right-hand Riemann sum. And then part B is let's evaluate the integral, the definite integral of this function. Exactly. Okay, so let's just see what these 2 parts, before we solve anything, let's see what they're going to represent. So A, this is what the graph approximately of this function looks like from 0 to 3. It looks something like this. Okay, I'm going to draw two copies of it, one for A and one for B, just so that we are clear on what these will represent. So the first will represent the signed area. So this area here counted negatively, this area here counted positively. Okay, so this signed area will be the integral. Okay, and then this signed area will be a sum of 6 rectangles with their right endpoints. So let's just divide this into 6 pieces here, like so, and we're going to get the following. So we'll have one right-hand rectangle here. This will be counted negatively. One right rectangle here. This will be counted negatively. Another one here. This will be counted negatively. This one here will be negative. This will be positive, and then the final rectangle will be positive. So the sum of, this area will be the Riemann sum from part A. So we'll count these 4 rectangular areas negatively, these 2 positively, and then the actual definite integral will be the exact signed area. So it'll be this exact area, and then it will be this exact area, and we will subtract this area from that area. Just looking at the picture, we expect that the answer will probably be negative to this question, because it looks like there's more area under here than there is here. This is just what's going on. This is the idea, so that you understand what's going on. Now let's do this. So let's do part A. So n equals 6, A equals 0, B equals 3. So our width of our rectangles will be 0, or I'm sorry, it'll be 3 minus 0 over 6. That's a half. Okay, and so what's really going on here is we've got an interval from 0 to 3. This is our A, this is our B, and we're going to divide this into 6 pieces, like this. So this will be x1, this will be x2, x3, x4, and x5. Okay, this one here, this is x6, and this one, if we're following our definition notation, this is x0. So we're interested in these 6 points. These will determine the heights of our 6 rectangles for part A. And we have a formula for xi. The right endpoint is a plus I times the increment. So that is 0 plus I times a half. So it's really just I over 2. Okay, so this is our xi. So we've got our A and our B and our 6 and our xi. So if we want to sum up the areas of these, we write down, we're summing from 1 to 6, and we're taking f of xi times the width. So this is the height, this is the signed height of a rectangle, and this is the width. Of a rectangle. Okay, again, let's just emphasize what's going on here. So each of these terms, when I goes from 1 to 6, so there should be 6 things that we're summing together here, represents a signed area here. So when I is equal to 1, this represents the width of this is delta x, and the height of this, well, it's a negative height, is whatever the coordinate is, and the y value at that point right there. So this will be 6. This will be 6 rectangular areas, and we can just write them out. So this is, we start off with f of 1/2, and we're multiplying by a half, plus f of 1, and we're multiplying by a half, plus f of 3/2, and we're multiplying by a half plus f of 2 times a half plus f of 5 halves times a half plus f of 3 times a half. So these are the 6 rectangular areas. And if you do this calculation out, so that is if you plug, remember our function is x cubed minus 6x. If you plug 1/2, 1, 3/2, all of these numbers into f and do this calculation here, then what you will get, I think, is minus 3.9375. Okay. This calculation is done in the book as well on page 303 if you want to follow along in the textbook. So this is the answer to part 1. Notice it's negative, which we expect because when we drew this picture right at the start, we saw, okay, there's a little bit more negative rectangular area here than there is positive rectangular area. So we get that. Okay, so that's the answer to part A. This is the Riemann sum with n equals 6 using right endpoint rectangles. All right, now let's answer part B. So we want to compute this definite integral using the right-hand definition of a limit of Riemann sums. So we're summing from 1 to n. Now n is not 6 anymore. N is going to grow without bound here. So we get, so we'll have, but the formula is the same, like this. Again, our xi is equal to a plus I times delta x. But in this case, delta x is a little bit different. Delta x doesn't have a 6 in it anymore. It has an n. So delta x is b minus a over n. And this is 3 minus 0 over n. And so that's 3 over n, like this. Now, let's take a look then. So xi is 0 plus I times 3 over n. A was equal to 0, so we get that. So this is, let's write it like this, 3i over n. This is the formula for our xi now. Okay, so let's write this down. What does f of xi look like? So this is the area of one rectangle, signed area. So this is equal to, okay, so we plug this value into here. So we get 3i over n cubed minus 6 times 3i over n. That's the signed height of our rectangle. And then we're multiplying by 3 over n, like this. Now, let's take a look at what this gets us here. So I want to simplify this a little bit because we're going to put it into a sum here. So this will simplify if we factor this out. We'll get 3 over n to the 4th power, because we're multiplying 3 over n times this, times I raised to the 3rd power minus, and then let's see, this is going to be, this would be 6 times 3 is 18, times 3 is 54 maybe. Let's do 54 over n squared times I. So this is what we get when we expand this out. And then we're summing then this expression. So the definite integral from 0 to 3 of x cubed minus 6x is equal to the limit as n goes to infinity of this expression. So we've got 3 to the 4th over n to the 4th times I cubed minus 54 over n squared times I. Okay, so all of this is meant to be accounted for in this summation, and then once we have an expression for this, we can worry about taking the limit of that later. Okay, so let's do that. We have equal, so this is the limit as n goes to infinity. All I want to do is simplify what was in here. Okay, so we get So we get the sum. First things first, if we take a look, this is a difference of two terms, so we can split that into two separate sums. So we get a sum I goes from 1 to n of 3 to the fourth. What is 3 to the fourth? I think it's 81. 81 over n to the fourth times I raised to the third power minus, and then this is 54 over n squared times I. Okay, so all we did was we just split the one sum into two sums. Now, we're going to use another one of our rules. This term, the only term that's changing as I changes here, is I cubed. This, for all intents and purposes, is a constant in this summation. And so we're going to treat it like a constant, and we're going to pull it out like so. So we've got 81 over n to the fourth came out here, and this is what's left. And then we want to do the same thing here. 54 over n squared is a constant. It'll appear in every term of this sum, so we're going to pull that out as well. Remember, as long as it doesn't have an I in it, it can come out of the sum if I is what you're counting. So I goes from 1 to n, and I, like so. Okay. Now we're going to use some formulas. And these are not formulas that I expect you to know. I will always give them to you. The first formula is what you get when you sum up n copies of the cubes. So this is 1 cubed plus 2 cubed plus 3 cubed plus all the way up to n cubed. We have a formula for this, which is n times n plus 1 over 2, and this whole thing squared. Okay, that's a simpler way of writing this, the sum of the first cubes. And then another formula here, which is the sum of the first n integers, which is 1 plus 2 plus 3 plus up to n. This is equal to n times n plus 1 over 2. Okay, so these are just some formulas we're going to use. Notice, so these are the pieces that we see in this expression here. So we're going to use these formulas to get rid of those summation symbols. And so this is equal to the limit, as n goes to infinity, pardon me, of the following quantity. So we have 81 over n to the fourth times, okay, now I want to replace this by that. So we get n squared times n plus 1 squared over 4. And then we have subtract 54 over n squared times, now we're going to replace this piece here by its corresponding formula here, n times n plus 1 over 2. Okay. Now, this looks scary, but it's just a limit of a ratio of polynomials. Okay, so we can think about this. If we think about it, this will be the limit as n goes to infinity of, so we'll have 81 over 4 times some quantity here that has n to the fourth in the denominator, and n squared times n plus 1 squared here. And the same thing here, let's do 54 divided by 2 is 27, so let's get rid of that. And then we'll multiply by n times n plus 1 over n squared. Okay. Now I want you to look at this very carefully. Let me just make sure this is appearing on the camera. It is. Okay. This is a limit of two ratios of polynomials. The highest power of n in the numerator here is 2, because you'll have n times n there. That will give you an n squared. And the highest power in the denominator is also 2. So as you take the limit of this piece right here, this will approach the value 1, okay? Because the n squared in the denominator and the n squared in the numerator will be the dominant terms in that limit, and so they will equal each other in the limit. Same thing here. You will have an n squared because n plus 1 squared will give you an n squared. And when you multiply that by n squared here, you'll have an n to the fourth, and that will cancel with this n to the fourth here in the limit. And so this piece right here will also approach 1. So we've got 81 over 4 times something that's going to 1 minus 27 times something that's going to 1. So the answer, the limit here, is equal to 81 over 4 minus 27. Okay. Now if you do this, if you compute this, then you will see that this is equal to minus 6.75. Okay. Negative again, because go back to our picture here. We expected there to be a little more signed area here than there was here, and so this is counted negatively, this is counted positively, so you expect the net answer to be negative. All right, so that is the answer to B. So the integral of x cubed minus 6x dx is equal to minus 6.75. This is the answer. All right, very good. Now let's do another example. So let's just set up the integral. Let's do 2 to 5 x to the 4th as a limit of Riemann sums. Okay. We're not going to evaluate it. We're just going to set this up to give ourselves some practice. The solution here is, well, we have a is equal to 2, b is equal to 5, and so that means that our delta x, our increment for this, will be 5 minus 2 divided by n, so that is 3 over n. Our right-hand endpoints will be a plus I times this increment delta x. A is equal to 2, so we get 2 plus I times 3 over n. And maybe if we're, that looks sort of silly. So we're going to write 2, 3i over n, like that. We're going to just bring that I into the thing. Okay, and then that makes the integral equal to the limit as n goes to infinity, a sum, I goes from 1 to n, and we need f of xi, so that is 2 plus 3i over n to the 4th. Sorry, that's a 3, and that's an n, 3 and n. Sorry about my bad penmanship here. And then we multiply that by 3 over n. And this is all there is to it. This is the answer. Okay. All this question asked for us to do was to set up the integral as a limit of Riemann sums. We did not evaluate it. So if we wanted to, we could evaluate it, but we're not going to. This is the answer to this. Okay. Let's do another example where we just use the geometric definition of the integral. So how about this question here? Evaluate using areas. Okay. So anytime you see a question that says evaluate an integral using an area, you don't have to use the limit definition in any way. All you have to do is know what the graph looks like and see if you can figure out what it is. Okay, so this is a graph, this is a line of slope 1 passes through minus 1. So this is minus 1. It's also going to pass through 1 here, 2, and 3. So we should get something that looks like this. This is this is what the graph of this function looks like. This is y equals x minus 1. And so we know that this should be counted negatively and this should be counted positively. Well, how much area is in each of these? Well, this is just a triangle. It's 1/2 the base times the height. So the base is length 1, the height is length 1. So this is 1/2 times 1 times 1. And this here is a triangle. 1/2 times the base length is 2, and the height is also 2. Okay, so our answer to this question will be we'll take this area, which is a half, but signed negatively, and this area, which is 2, but signed positively, and so the answer to this is 3/2. Okay. Notice we did this without any limits or any Riemann sums, anything like that. All we used was the fact that the definite integral represents the signed area under the graph of this function between these 2 points. So these can be pretty easy to do if you have the right graph. Now, let's go through some properties of the integral. So properties of the definite integral. Okay. Property number 1, if c is a constant, then the integral from a to b of the constant is equal just to c times b minus a. Okay, let's see this with an example. So suppose that c is equal to 2, a is equal to 1, and b is equal to 4. So what is this, this integral? So this is, here's a is 1, b is 4, and the constant is 2. So this is what the graph of the function y equals 2 looks like. Okay. Now how much area is under here? Well, it's just that length, which is 4 minus 1, times this height, which is 2. So we get 4 minus 1, which is 3, times 2 is 6. So that means the integral of 2 dx from 1 to 4 is equal to 6, which is c times b minus a. So that's property number 1. Okay. Property number 2 is same situation. If you have a constant being multiplied by your function inside of the integrand, then that constant can just be removed. Okay. So as an example of this, suppose we looked at our last example. We had 0 to 3, and we had 3 times x cubed minus 6x, like this. Okay. We know what the integral is of x cubed minus 6x. We just computed it. It was like minus 0.675 or something. So we could solve this by pulling this constant 3 out. And this will be 3 times minus 6.75 is our answer. So that's property number 2. Property number 3. If you take 2 functions and you subtract or add them from each other, and you want to compute this integral, then this is exactly the same as just splitting this integral into 2 pieces. So whatever that sign is, plus or minus, you can make it, and you just make it plus or minus here, and you can solve this example in exactly such a problem in exactly this way. So if you're adding or subtracting 2 different functions inside of the integrand, then you can split that integral into 2 pieces. Okay. Another case, if you're integrating from a to c, and you take b to be any point in between a and c, so let's do it this way. So let's say this is the graph y equals f of x. So the integral from a to c will be this whole area here. The integral from a to b will be that area, and the integral from b to c will be that area. So we can split this into 2 different integrals. Okay, so that is to say all of the area, which is represented by this, is equal to the sum of these 2 separate areas. So the integral from a to b is that one, the integral from b to c is that one. Okay, this is just a very common sense property. One other, this is just a convention that we will probably use from time to time, and that is that if you have the integral from a to b, then if you were to reverse it, if you were to switch these endpoints, then all it affects is that. Okay, this is just a convention. It's sort of like going backwards versus going forwards. Like here, if a is less than b, then this integral captures the area. But if you go backwards instead of going forwards, then it's sort of like we count that as negative area. Okay, so this is just a conventional rule. All right, we're going to talk on Thursday about various problems related to integration, and so we'll cover any issues that come up related to section 5.2 then. And the next section will be 5.3.